All right, so let's take a look at how do we find the electric field from a charge distribution, not just from point charges. So remember the basic idea from a point charge, right? We're gonna use the electric field. The contribution electric field is kq over r squared, right? From an individual charge. But so if we're gonna do what we're gonna do if we have a charge distribution is we're gonna chop it up into little pieces, right? We're gonna chop it up into a little charge called dq. And then the contribution of the electric field is k times that charge dq divided by the distance squared. Now, here's the tricky part, right? K is a constant. R may be a constant. It may vary. Kind of depends on the distribution. May depend on the dq. Maybe the dq and the r are dependent on each other in some way. But we got to get all of this in terms of one variable so we can do the integral. The other part is this is a vector. So when we add them up, we got to add them up like vectors. That means we have to decompose this thing right here into horizontal and vertical components and only add in the components that are pointing in the same direction. So we got to keep that in mind. We can't just simply plug in the integral because these are vectors. And remember, an integral is like a sum, right? But we're summing vectors, so we need to treat them like we're summing vectors, not summing scalars like we normally do in calculus. Okay, so a lot of times we have a large linear charge density. Sometimes you'll have density times the length or times the area times the volume. For a linear charge density, for a surface charge density, like a linear charge density means it's a density per length. So you take the density per length times the length to get the charge. If you have a area density or a surface density, then you got to multiply it by an area. And if you have a volume density, you got to multiply it by the volume to get the amount of charge. So we'll go through some examples when we kind of go look at this. So if the charge per unit length on the semicircular wire is shown below is lambda, okay? What is the electric field at point P? If the total charge is positive, what direction is the electric field? Okay, so first step, what is the electric field at point P? So first step, we're going to chop it up into little pieces. So we got to chop it up into a little piece here and say this is dq. Okay, and so then the electric field from this, let's assume it's positive. Okay, we don't know if this density is positive or negative, but let's just assume it's a positive. That means the contribution of the electric field from this charge, right? The electric field is pointing away from the charge, so it's going to contribute we call it dE, the contribution of the electric field from that charge here. And then similarly, if you go over here, like there's another dq over here. Like we're gonna chop this thing up into tons of dqs, right? So you gotta think of it as like you're chopping it up into tiny pieces, and each piece is a point charge in itself, and we're gonna add them up. So this guy over here is gonna contribute a dq along this axis away like this, and so you gotta think about adding them all up. Now here's the thing, horizontally, hopefully you can see by symmetry, because you're gonna have a piece over here that's gonna contribute this way, and a piece over here that's going to contribute this way, the net electric field is going to point upward in the vertical direction. All the horizontal components are going to add and cancel each other out because you kind of have the symmetry on the left and the right side here, right? So we want to think about, so first of all, dE is going to be k dq over r squared. Now in this case, the dq, the charge, is lambda times the length. We'll call this dx, I don't know, for lack of a better word, dx, divided by r squared. Now, the distance from the charge to there is just r, right? And it's the same r because it's a semicircular part. This r is a constant. It doesn't change, right? What I mean by constant, it means it's the same for every piece of charge. Now, if this were a straight wire, or we were picking a different point here, then the distance to those charges are going to be different. But because we're picking the center right here, it's equidistant. So that means this r is a constant here. Now, we need to consider only the vertical component. So let's look at one representative one. So I'm going to erase all these other ones that I drew. And we're just going to focus on this guy right here producing this electric field. Now, I want to decompose it. Need to decompose it into vertical and horizontal here. So this is the dE in the y direction. This is the dE in the x direction. I don't care about the x direction because I know by symmetry that's going to add to 0. So I only care about the y component, right? And remember how we decompose that is we're going to make this a theta. And so we're going to say dE in the y direction is going to be dE, say, cosine theta. Well, say, yeah, cosine theta, right? Because that's the adjacent side, all right? And that's going to be k lambda dx over r squared times cosine theta. Now we would want to integrate this, but unfortunately we have two variables here. One is dx and one is cosine of theta. And that's not going to work because theta is going to be varying a little bit, right? And if you just be very clear the way we define theta, this here, at this point down here, theta is equal to 0. And at point over here, like if I draw this part, right, that's my dE field. And that theta, just the way I did it, this theta over here is going to be like, 90 degrees or pi over 2. We'll call this negative pi over 2, maybe. You could call it pi over 2, negative pi over 2. It doesn't really matter because that will just change the sign. And we already know the direction of the electric field. And over here, it's going to point this way, and we'll call that so we'll say this is pi over 2, this is negative pi over 2, and this is theta. Now, but we have dx here instead. Dx being like the length here. Right, so we got to relate that to the theta, and this is where we may have to understand a little bit about polar. But one of the things about arc length, if I draw a little shape like here, and this is from your pre-calculus days, you should know that the arc length, if you do things in theta, if this is d theta here, okay, this little angle slice here, then the length dx is equal to r times d theta, right? This is arc length. So this goes back to some pre-calculus area where we say like, oh, if I know this angle theta, then this distance here is r times theta. Okay, so that's the same thing there. So we can replace the dx with r and d theta. So we'll get k lambda r d theta over r squared times cosine theta. The r's will cancel. And now we can have k lambda over r d theta cosine theta. And now we have when we integrate this, so this is dE and the y component, we're going to sum them all up. When we sum this all up, this is the only variable. These are all constant, right? So k lambda over r. Remember we talked about why r is a constant because it's the same r for all the charges. And so we're just going to integrate cosine theta d theta, and we're going to go from negative pi over 2 to pi over 2 because that's how our theta was set up. So yeah, it's like a little bit tricky on the setup, but you just break it down to pieces. So this is going to be k lambda over r. Integral of cosine is what? Negative sign? No, just positive sign. Sine theta from negative pi over 2 to pi over 2. And you can use your calculator for that, honestly. This is not a math class. That's going to be sine of pi over 2 is 1. That's going to be 1 minus 1. That's going to be 2. So it's going to be 2k lambda over r as our answer there. And the electric field is, because it's positive, it's going to be pointing upwards. Okay. Let's do another one here. So let's say a total charge Q is distributed uniformly. Uniformly means that like the charge is spread out. So an entire Q is over this rod. Like they'll set up the integral to find the electric field at point P, P1. Okay, so P1 over here, we want the electric field at this point here. Okay, so again, the density, they didn't give us to us, but it's charge per unit length, right? And it's a uniform density. So we can do this in terms of the linear charge density. We're also going to chop up into little pieces. So we'll just take a representative piece here, dq, and consider the electric field it generates. And let's assume it's positive again. It's pointing away, right? That's the contribution of the electric field pointing away from that charge. Right, and if you think about all the charges because of the symmetry here, right, some are going to be over here, some are going to be pointing up, but ultimately we're only going to care about the component pointing vertically. Okay, so then we say like, okay, cool. So I only care about the vertical component, so I'm going to decompose this, and I only care about this one. We'll call this theta. This is dE sine theta, and I'm only going to add up the vertical components because the horizontal components are going to cancel each other out. So dE, which is a vector, is going to be k dq over r squared. That's going to be k. What is the amount of charge that's on that dq? Well, it's lambda times the length there, divided by r squared. Now, in this case, the r is not constant because the r is the distance from there to there, right? So a charge over here is going to have a different r. So we're going to need to put our r in terms of various expressions and probably in terms of theta, right? So this is going to be dE sine theta, because we're only going to consider the y component, right? So it's going to be k lambda dx over r squared sine theta. Now, we probably want to put everything in terms of theta. Kind of varies. You could try to put everything in terms of x if you wanted to. Let's just you can, because this is nice, let's make this x equals 0. So we'll make this x equals negative L over 2, and we'll make this x equals L over 2. So we're making right the positive direction, right? Because we're going from negative to positive there. That's just sort of convenience if we're going to use it in terms of x here. So one thing that's nice is let's look at that distance here. So we're going to call this distance from here to here. By doing this, we're saying this distance from here to here, we're going to say is x. Okay, and this is a over 2. So we know what r squared is. R, or at least because of this right triangle right here, right? This distance, r, is going to be the square root of x squared plus a over 2 squared. Okay, cool. And we also know this is theta. So one thing that we can make this easy is we can figure out what sine of theta is. Why is this theta? Because it's like a corresponding angles, or I forget the term for it, but these two are the same by similar triangles, or two parallel lines, if you will. So sine of theta we also can convert in terms of x. It's going to be opposite over hypotenuse. It's going to be a over 2 over r, which is a over 2 over this r, which is square root of x squared plus a over 2 squared. Okay, so see how it's complex, but we want to take each piece at a time. Okay, so k and lambda are constants, so we don't have to worry about that. Dx is there. Now r squared is this thing squared, which is x squared plus a over 2 squared. And we can get rid of the square root because that's r squared, right? So if I square that, I would get rid of the square root. And sine of theta is going to be a over 2 over square root of x squared plus a over 2 squared. Okay, and then we're almost done. We just got to replace the lambda because the lambda wasn't given in the problem. We got to make that q over L. So then we're going to integrate that, but replace that with q over L. So we're going to integrate this k q over L dx times a over 2. My a's are awful. It's not a 9. It's supposed to be an a. And this is supposed to be a q. Okay, cool. And then this times this, because this is to the first power, this is to the 1/2 power, you can make that just to the 3/2 power. Because 1 plus 1/2 is 3/2. And then we're integrating over the letter dx. And so what does the range of x need to be? It needs to go from negative. We're going to do all the charges from here all the way to here. From negative L over 2 to L over 2. And so that would be the setup of the total electric field. In the y direction, and in the x direction, it ought to be 0. You can do this exercise to try to set for P2. That's probably another problem. Okay, let's look at a ring charge. Ring charge is a little bit trickier. So we have a non-conducting ring of radius r shown lies in the yz plane like this. So it's like the ring is, this is the outward arrow from the face of the ring. Carries a uniformly distributed charge dq. Show that the x component of the electric field on the axis is given by this. Okay, so let's take a look at this. Now, here's the thing. We're trying to pick a point along the x-axis. So let's call this distance x here. Now, we're going to chop this thing up into little pieces, little charges here, dq, right? Just like this. And this is going to create an electric field radially outward this way. Now, this one's a little trickier because you have to think about the electric fields are going to be pointing away from this charge, but it's along this axis. So like what's going to happen is all the vectors are going to be kind of like, if this is like a line here, they're going to wrap around like this, all the components. So hopefully you can see by symmetry, the net electric field is going to point this way, right? DE in the x direction, which is all we actually care about. They're actually only asking about that anyway. But the other components are going to cancel each other out here. So if you draw a line from here to here, right, and then this is theta, then what we need to do is then say like, oh, okay, so we need to find DEX. So first of all, the DE is going to be K dq over r squared. Now the r is the same because the distance from here to here is the same everywhere, and that's K dq would be would be the charge density. Lambda is going to be q divided by the entire length of the ring, which is 2 pi r, right? Because the charge density is the amount of charge divided by the length. So it's going to be K lambda. We'll call it dx. I don't know. Well, x is probably not a good word. We'll call it dr. Well, dl. Okay, so we'll call this distance here dl. Divided by r squared. Well, this thing is a fixed distance away. It makes a little right triangle here. It's going to be, this side here is going to be the square root of x squared plus r squared. And it's going to be the same, square root of x, and then you square it, so it gets rid of the square root. x squared plus r squared, right? So this is r, but when you square it, it gets rid of the square root there. Okay, now we only care about the x component, right? So it's going to be k dq over r squared times this component here, we'll just say cosine of theta, right? Because when we decompose it, it's going to be here and then here. We only care about this angle here. How do we figure out this theta? Well, this theta matches this theta. And what is cosine of theta for this triangle right here, right? Because this is vertical angles. So then we're going to say cosine of theta is going to be adjacent, which is x, divided by the hypotenuse, which is r, which is the square root of x squared plus r squared. Cool. So then we're going to plug that in. So the dE in the x direction is k dq, or we'll call it, sorry, lambda dl. That's what we replace the dq with, lambda dl, right? Divided by, technically r cubed, r squared times, but we'll just say it, this part was x squared plus r squared, and then x over square root of x squared plus r squared. Okay, cool. Now, this x is like a fixed point in space because it's a function because it's a function of the distance. But like when we integrate, when we add up all of these charges, these dq's, to get the total amount, the only thing that's not fixed is the dl part, right? So what we're going to have here, this is going to be k lambda x are all constants. This is to the first power. This is a 1/2 power, so this is x squared plus r squared to the 3/2 power. And then integral of dl. Integral of dl is just adding up all of the length dl's, right? dl, if you add up the length, that's just literally what the circumference of the ring is. So this integral right here is literally 2 pi r. It's the circumference of the circle. So we're going to get k lambda x over x squared plus r squared to the 3/2 times 2 pi r. And the last thing we want to do is get our lambda, which is the charge per unit length. That's the q over 2 pi r, right? So that's going to cancel that if I replace it with a q over 2 pi r, that's going to cancel with this 2 pi r. And so we're going to get kqx over x squared plus r squared to the 3/2. And that's exactly what, oh, okay, so the k, remember, is 1 over 4 pi epsilon naught. That's the relationship there. But we get the same thing in there, okay? So that's how we do it. A little bit tricky, but you want to practice that kind of setup, chopping it up into pieces and finding expressions for in there. That's the challenging part of using calculus in physics. Thanks for checking out this video. I hope you found it really helpful. If you'd like more support, maybe you need more multiple choice practice, maybe you just need more guidance and things like that, I have plenty of information on my website. If you look in the description below and go to www.bothellstemcoach.com, I will explain all the ways I help students be successful in their AP classes.